Hey, my name is Stan and I'm part of the Outflank team. We are a unit within Fortra that creates a offensive toolkit for red teaming operations and attack simulation, and it's called Outflank Security Tooling, or OST for short. It's a toolkit which includes capabilities for initial access, a C2 framework, and various post-exploitation options such as credential dumping, some fake ransomware, a hidden VNC module, and much more. In today's video, I will focus on the C2 framework, which is included within OST, which is called Stage 1. So let me take you to the portal and demonstrate how you can use it. We go to True Phase, and the first thing that we have to do is we have to download a fresh copy of the C2 server. Because although OST is a cloud-delivered toolkit, of course, you want to maintain control over your offensive infrastructure. So you as a red team, you will download a fresh copy of the team server. It is contained in a Docker container, and you deploy that as a listening post in your own offensive IT infrastructure. You configure your redirectors, etc., and then you're all done from a C2 server perspective. After setting up the C2 server, you have to configure your implant. So for that, we go to this option within the portal. We select the project that we're currently working on, and then we have this workflow that we need to go through to configure the implant. First of all, we need to define what the communication from our implant to the listening post should look like. So we could use HTTP or HTTPS, including options for domain fronting. We can do SMB or name pipe communications, which mostly makes sense for internal command and control. TCP communications or file-based communications. And file-based communications are a very good method. For example, if you have targeted two systems within two network segments which are firewalled from each other, but they can both access the same file share. In that case, you can use file-based communications to still set up C2 communications between these two network segments. In this case, let's focus on HTTP or HTTPS, which is very typical for your initial access implant. Of course, you can configure multiple channels if you want to. You can configure what the request, etc. looks like. You can configure the user agent, and we also have some options which you typically do not see in other C2 frameworks. For example, we support SSL public key pinning as well as SSL CA pinning to make sure that the configured connection does only run on the expected route, and for example, not if the connection is being SSL intercepted. We also have various other implant settings, mostly focusing on OPSEC. So for example, we can use hardware breakpoints to bypass MZ as well as ETW logging if you're later going to do things like executing .NET assemblies. We can disable control flow guard for process correction. We can clear the PI callback for process instrumentation callback, which helps you evade detection of the use of direct system calls, and various other OPSEC features, including ROP gadgets and RIP allocations, which are some really nifty tricks for bypassing memory scanners of EDR products. So hearing all of this stuff already hints on why you would want to use Stage 1 C2, despite your team probably already using another C2 framework such as Cobalt Strike. Why? Because they can work closely together. That's also why it's called Stage 1. So in our workflow, we typically come in with a initial access malware artifact, for example, something which is created via OST's payload generator. We use the payload generator based artifacts to execute our shellcode in a OPSEC safe way, and the shellcode which we execute is typically a Stage 1 C2 shellcode first. Why? We're going to land on a system where we do not know that many about. we might not know which EDR product is running there. We might not know what security settings are configured on that system. So we need to come in as OPSEC safe as we can. That is why we deploy stage 1 first. We can then leverage stage 1 to do recon on the system and find out all of the security measures which are configured there. And as soon as we understand the system, we can use the injection mechanisms, which in stage 1, to safely inject our stage 2 C2 framework, such as, for example, Cobalt Strike's beacon. So after all of this configuration stuff, I can finally click build. And if I click build, I can then send the shellcode to, for example, payload generator, or I can download it from the portal to integrate it with any of the custom tooling that your red team might have. I've previously done this. So if I go to my target system, demo, double click the CPL file, which I've previously created, we should then see a implant coming in our C2 server. There it is. So the C2 server is no longer running in the portal. You can tell it from the URL right here. It is running in our own offensive infrastructure, and we just have this implant coming in right here. The implant is fully automatable via Python code. So for example, if you want to execute steps upon initial check-in of an implant, you can just code that in Python. If we type help, you see that we support beacon object files, so you can include all of the beacon object files that you like. And we have a number of building commands, especially for local reconnaissance. So for example, with the config command, I can check whether my C2 connection is currently being routed via a proxy or direct. And I can check whether I'm being SSL intercepted, yes or no. In this case, we're not. I can do an extended process listing to identify any of the security products which are installed on this system. And eventually, after I understand this system, and I might need some capabilities, for example, in a more feature-rich command and control framework such as Cobalt Strike, I can use the OPSEC features within stage 1 to safely load a Cobalt Strike beacon temporarily into memory. So with exec shellcode and exec shellcode thread, we can see that we can load a Cobalt Strike beacon within the memory of the host process of stage 1 and also apply a sleep mask to the Cobalt Strike beacon. How neat is that? So that we can evade any memory scanners via this feature. So within Cobalt Strike, I go to payloads, generate all payloads. There we go. Awesome. Then back to stage 1, exec shellcode. Within the current thread, apply a sleep mask. I can choose the specific shellcode which I want to execute. And let's select a exit thread one. There we go. Execute. We can wait for the next check-in. It says success. So if we now go to Cobalt Strike, there we have it. We have a new beacon coming in. So I can execute any of the commands that I want to execute in Cobalt Strike. And as soon as I'm finished, I can do exit. It's an exit thread shellcode. So my thread will exit. Stage 1 can clean up the memory of the Cobalt Strike implant. And if I then go back to stage 1, I can see that in this case, the implant is still running over here. So via this method, I built this chain of trust where I first come in with a stage 0 implant, which has been generated with payload generator and all of the OPSEC features that provides. We can then load our stage 1 implant. which supports some OPSEC-safe injection methods to temporarily load Cobalt Strike into memory. I do my actions on objectives. I fly under the radar of a memory scanner via tricks such as sleep masking, etc. And then, if I exit the threat of the Cobalt Strike payload, it's no longer in memory, and we can continue, or we can fall back to our stage 1 implant, for example, for a long haul connection. Hope this makes sense. Hope you enjoyed this video. Thanks for watching, and if you want a demo of other capabilities in our OST toolkit, make sure to request one from our website. Thanks.